Hello everyone. In this video, I want to share with you my 2-year experience in doing RAG applications. In these 2 years, I tried many ways to do RAG. I also tried using agents to make my RAG application work better. However, using agents made my RAG application very slow. So at the end, I have to abandon them and to use something which works faster. In this video, we will go through the main 3 steps in RAG. So first, collecting our data. So for example, you may want to use some PDF files or HTML files. So the first step is to convert these PDF files to text files because LLM embedders understand only text. So in this example, I will be showing PDF files. So for that, I will be using by mu-PDF for LLMs. If you are using HTML, then there are other libraries to do that, namely to change HTML to markdown. I will put some links below this video. Then the second step is chunking, and chunking is important if you have big files. So imagine that you have a whole PDF book. So this book will be very large. So if you want to feed a whole book to the LLM, that will be difficult and very slow. There are mainly 2 problems here. The first problem is that maybe the LLM context does not even allow the whole book. So what will happen in this case that, for example, Olama or the library which you are using will cut this book and will feed only part of it to the LLM. And even if your library were able to feed the whole book to the LLM, that will require a lot of time. So to avoid that, we use chunking. So chunking is good because it splits your data into small chunks, and these small chunks are focused about specific subjects, and that will help you not to clutter your LLM input. So imagine that you feed a whole book, but your question is answered in 1 page of this book, and this book may be like 500 pages. So then you already like fed 499 pages, which may be cause the LLM to be lost and not find the correct question. So in chunking, I will be using semantic chunker. I will speak quickly about it. In my opinion, this is the best way to split your data. Then the third step is to use this data, namely to query or ask questions about this data. So our chunk data will be saved in a vector database. In this tutorial, I will be using ChromaDB. There are other databases out there. You can try them if you like. Then I will show you my last recommendation here about augmenting your query. So what happens usually is that the client will ask questions about the data. The first step here in RAG is to go and search our database about the corresponding chunks and then using these chunks to answer the question. In augmented queries, the first step here is changed. So instead of using the user's question to search our database, we will augment this question first. So for example, we can ask the LLM to answer the question and we will augment this answer to our query. Then we will search for the corresponding chunks in the database. Another option is to ask LLM to reformulate this question. So we got now a new reformulation. We can use now the question and the reformulation to search our database and find the corresponding chunks. And believe it or not, I found like this approach to enhance our search a lot. So without further ado, let's start looking to the code. So here I opened VS Code. I have the repo for this video series. You can see our code here from video 3. And now I made a new folder here for our current video. So here's our code. As you can see, I split this code into 3 Python files. Each one of these files corresponds to one of the steps which I showed in the introduction. There are 3 folders here, as you can see. The first one is the PDF folder. This PDF contains our data which we want to ask about. I chose a theme which I know very well, which is direction of arrival estimation. So I will say a few words about it if you are not familiar with that. So direction of arrival estimation deals with the following problem, assuming that we have multiple antennas. So a system like a radar with multiple antennas and having multiple sources of electromagnetic waves. These electromagnetic waves will reach the antennas here and be sampled using analog to digital converter, and corresponding signal will be used to determine at which direction this source is. This is very helpful in communication. So in this paper, they are talking about multiple methods. They are reviewing some history and talking about some new methods. I will be asking namely about 2 of these methods. The first method and the most known one is the music algorithm. Music here stands for multiple signal classification, and then there is the split algorithm, and split stands for estimation of signal parameters via rotational invariance techniques. That's enough about this file. Let's go to the first step. In this first step, we will convert this PDF file into a markdown. As you can see, I already prepared this here, so I will delete and let's go through the code. As we've seen in the introduction, this code uses by mu-PDF for LLM. So for that, you need first to install this package. So for me, that's already done. I use this command here. Then I prepared these two small functions. So the first function will simply take the PDF file. So here we have only this PDF file here, and then it's assuming that the path is known. So this is this PDFs folder here, and the output file will be written inside this markdown folder here. And then as you can see here, we are opening the output file where we want to write our output. And then we are simply calling the PyMo PDF for LLM and to markdown and giving it the path for the PDF folder. That will give us back the markdown text. Then I'm running the function called clean PDF text, which is here. I'll go quickly through this function, and then we are writing this to the output file. That's it basically. And the purpose of this clean function is to remove unknown characters. So what I noticed that when you are using text which are not English, we are getting some weird symbols, which is not very helpful and will confuse the LLM in the RAG. So here I'm trying to remove some of these characters. And my advice to you here is that whenever you generate data, please take a look at this data. So most of the time you will get things which we as people will not be able even to understand, and then you can only imagine how this will affect your output. The main code here is very simple. So here we are listing all the PDF files inside this PDFs folder, and then file by file we are calling the extract text from PDF function. So let me run this code cell by cell. So this is the first cell, only the definitions. Now let's run the main part, and it's done. So we have our markdown text. So let me make this part here bigger. And as you can see, it seems okay. So there are this styling characters here in markdown. So here we have, for example, this hash and these characters here, which are used in markdown to style the text. And then as you can see, we have the title here, the name of the author, then the abstract, and so you already can see here some data which may be cluttering, maybe which you want to remove. I don't know if this is important for you or not. And then we have the introduction, literature review, and so on. I want quickly to go through it just to see if there are some parts, for example, which one can remove. So you can see there are new characters which appears here. So maybe you want to delete those. Or if you think that they are important, maybe you want to find a better way to include them inside this text file. So for me, I will delete these. It's clearly those are the equations and are not extracted in the correct way. So I will just remove them here. I will keep the equations which look a little bit helpful. So this looks like the signal model, the steering array, and so on. Yeah, which is okay. I mean, these equations are okay also here. Here's also another confusing section. I will remove it. And then here we have the references, which is okay. So as you can see, you always need to look at your data. So let me save this file and let's move to the second step, which is chunking. So as I said here, I will be using semantic chunker. So the semantic chunker I'm using here is coming from langchain, and this chunker will simply take the text and split it based on some characters, for example, a full stop or a question mark or exclamation mark. You can also put here whatever expression you want to split on. So in this splitting step, as you will expect, text is split almost sentence by sentence or maybe even smaller. So the chunker now will compute the embeddings, the vector embeddings for each sentence, and will compare it to the consecutive sentences. So let's say now we are in the first sentence, we computed embeddings, and then we compare this embedding for the embeddings of the second sentence, if they are close each other and close here based on a certain threshold. So if that happened, then the semantic chunker will join these two sentences and move to the third one, and then we'll compare it with the embedding for these two sentences and so on. So the first line you see here is the threshold which I was talking about. So basically this BTAS, which stands for breakpoint threshold amount, and S for the plural. So I start by a high threshold, 95, and then go all the way down to 1. So by starting by a high threshold, I'm telling the chunker that I want the sentences to be really different from each other to split. So using a high threshold like 95 will result in larger chunks, because this will require that the two sentences to be really very different from each other to split them into different chunks. So that's why I start by the highest, go down to 1, and that's why I have multiple thresholds here. So what I will do, you will see it here later, I will be starting by the highest threshold and see if using such a threshold I can split the data, because that would be the best way to split the data. But if I was not able to split the data to the length which I want to use in my RAG application, then I move to a smaller threshold, and so on. Here I have a tolerance length, for example, which is 128 character, and this is the max length of the chunks which I require. So in this tutorial, I'm requiring my chunks to be 512 character or less. I always add this tolerance here because I don't want to be like a hard split by 512. So if it was like 550, that would still be okay for me, yeah? But not 1000, for example. That's why I'm using this extra token length here, yeah? Also, the name of the variable maybe does not represent that. I should have called it like tolerance. Then here I'm defining the character which I'm using for splitting, and as you can see, this is like a regular expression. So I'm using multiple spaces here, so 2 spaces or more, then new line characters, and then full stop, question mark, and exclamation mark. You can put here whatever expression you want. That depends on your data, of course. Here I am constructing now the chunkers. As you've already seen, I'm using the semantic chunker from langchain and a Hugging Face embeddings. Of course, here also you can experiment with other embeddings. So this step here will create 7 semantic chunkers corresponding to these 7 thresholds. And here again, I'm creating another 7 chunkers corresponding also to these thresholds. However, I'm using a different method to decide for the breakpoint. This method here is called gradient, while here in the previous line I was using percentile. And then in line 33 here, I am joining these two lists of splitters, as you can see here. So first I'm taking the chunker for 95 of this first list, then the 95 of this list, then the 90 from this list, then the 90 from the second list, and so on. So basically I want to start trying, as I said, from the highest percentage. That's why I use first the highest threshold from this list, then the highest from this one, and so on. So now here I'm defining this max depth. You will see why I'm using this here inside this function, split all chunks at once. So this split function, it will take the text which we want to split and the depth. And the depth will be basically the index of the chunker which we should use. At the beginning, we should start by the first chunker, which is the chunker with the percentage 95 and using percentile. So that's what 0 here means basically. And the 1 would be using the gradient, but also the 95% and so on. So let's go quickly through this function. So as you can see here, first, if this text is empty, we are returning an empty array. If the text is smaller than this buffer, which is like 128, then I'm raising an exception because we also don't want a very small text. Imagine that you split your text such that each sentence is a chunk, and then you use only one sentence to answer the question. So here you either get too lucky and already this sentence answer the question, or you'll just get wrong answers. So basically, smaller chunks is also not required. I would say even maybe worse than longer chunks. So longer chunks will only cause slower performance, while smaller chunks could break the whole system. Here also I'm testing the depth. So basically, if we tried all the chunkers, then I'm also raising an exception because that means I cannot split this text easily. So in this case, the best thing to do is maybe to look at the text and really try to split it by hand, or just by introducing also new characters to split on. So then, as you can see here, I am simply taking the corresponding chunker and we call the function split text. We pass the markdown text for that, and this will give us chunks. So this is a list of chunks. Then here I'm computing the maximum length of these chunks, so length of the largest chunk. And if this is larger than my allowed length, so basically this 512 plus 108, then I will call this function and will increase the depth by 1. So I will use the next splitter. And if all the chunks have the required lengths, then I will simply return the results. Yeah. So as you can see here, I'm returning the chunks, the depth. So this will tell me the used chunker and some more information about the chunker. To be honest, I have not used this yet, but I have like in my mind some purpose for this output. So let me tell you what I have in mind here. So if we were able to split the text using the first splitter here with 95 percentage, then that's okay. That means really that this chunk, the current chunk, was really not very close to the chunks which follow it. However, if we ended up like splitting using a splitter with a threshold like 1, that means the consecutive chunks are very similar, and maybe we want to include not only the current chunk, maybe the chunks after it, or maybe 2 of the chunks after it, or maybe also the chunk which comes before it. So that's what I had in mind. I have not applied this here. Maybe you want to do that and try it. And that's why I'm returning this data here. And as you can see, so this chunker used will just return some extra information about parameter of the chunker here. So this is here now the main part of this file. So basically it starts by listing all the MD files. So here we have only one, and then it enumerate over these files, and every time it read the whole text first, and then it called this function split all chunks at once, which would return the chunks, depth, and all the other parameters of the chunker. And as you can see here, we are appending those chunks to a list called chunk docs, where here we started with empty list, as you can see. So when this step is done, we already have all our chunks. We need now to save them in a vector database. And in this tutorial, as you can see, I will be using ChromaDB. So you also need to install ChromaDB if you don't have it. So here in this install command, I included langchain and community and langchain experimental, but not ChromaDB. So let me add it here. So then you will have all your packages. And now the first step is actually to define the collection name. Here I'm using direction finding plus the maximum length of our chunk. So that would be now direction finding 512. Then we create a persistent client because we want to save this to a database. And as you can see, this will be added inside the third folder here, DB. Then as you can see here, I'm deleting the collection. So this is just in case you are experimenting a lot and you already created the collection, but you want to rerun the code once again. It's better to delete the collection first. So after deleting the collection, I'm creating it again. So now we start with a fresh new collection called direction finding 512. And then I'm simply enumerating over all the documents and all the chunks of each document. In our case, this outer loop will have only one document, but it's still there. I mean, in case you want to try using multiple PDF files. And as you can see, inside the inner loop, we're simply adding our data chunk by chunk. So for each chunk, we are adding the corresponding text and then some metadata. This metadata includes the title, then the depth of the chunker, then the length of the chunk, and all the other properties which I got from the chunker. And that's it. So let's run this code cell by cell. So start by the first cell with only some definitions. So this first step will take some time because we are creating 14 chunker. So I fast it forward. Then we have the second step, which will also take some time. Here we will try to split the file using the first chunker. Then if that works, we'll stop. If not, we will use the second chunker and so on. So I will also here fast forward. So now it's finished. You can see now how many chunks we've got. So we have one document with 4 chunks. Let's now run the code to save it here inside this DB folder. So you can see now it started adding the files here. You can see that ChromaDB by default uses SQLite 3 as a backend, and this would be our document. So these are the chunks of our document. So it seems that we have 253. Yeah, so let me clear this. So this is because I computed the wrong length. So basically this 4 was the length of the table which contained the chunks, the depth, and the other metadata. Let me show you the correct length here. So we are in this chunk documents. So we only have one document. So let's take the index 0. And you can see now there is a title, then chunks, and then the metadata. I think then the depth and the metadata. So what we need to do is to take the chunks, and I should have computed the length of that, which is, as you can see here, 253. So now we have our data saved here inside this vector database. We can go to step 3, which is querying this data. And let's go quickly through the code. So first, we are putting the name of the collection, direction finding 512. Then again, we are creating a persistent client. So because we need to load the data, and then we're getting the collection which we want to use. And we have only one function here, as you can see, it's called query, which will take a question and a number of results, which I put here to 10. So basically how many chunks we want to return. And here we are using a function from the collection. So this function called query, it will take the list of questions we want to ask. Here I will be using only one question and the number of results which it will return. So here it will return for us, for example, 10 results. These results will have like IDs, distances, so the distance of each corresponding chunk from the given question here. Then we have the documents, so the text corresponding to each chunk, and then the metadata. So simply we are returning this data here. So let me run this cell here, and let's move to the second cell where we are trying a question. So what's the split algorithm for direction of arrival estimation? We are putting now some options, so the temperature to 0, and we are using olama.chat. and the llama 3.2 with 1 billion parameter. As you can see here, we are asking the question directly and printing the answer. So that's without using RAG. Let's try that, and let me make here bigger. So this is the answer which we got. So here it thought that this esprit stands for estimating of source parameter in radio interference, which is wrong. And then it goes on talking about this, which is also wrong. It also like hallucinate and says, okay, this is also used for direction finding and so on. But this is really wrong. So we know that esprit stands for estimation of signal parameter using rotation invariance technique. So there is no mentioning here for the rotation invariance technique. And now let's see the next part here where we are using the RAG. So basically we are passing this question to the query. So now we will get 10 results. So we'll get 10 IDs and documents and metadata and distances. I'm just printing the distances and the first document and metadata. Then here I'm preparing a prompt. So you are a helpful assistant and so on. So you answer a question based on the given context and so on. So then I'm putting the given context, which is simply joining these documents using a new line character, and then I'm question, and then answer, then semicolon. So just to let the LLM start generating the answer, because I will be using the generate function and not the chat. Yeah? So here we will simply like calling llama.generate using the same model as before, using the same options as before also. So let's see now the output. So this is the information we got from the query. And now this would be our answer here. You can see that the esprit estimation of signal parameter via rotational invariance technique. So the RAG is working, yeah. Then it's talking that this is a method for direction of arrival estimation. It does not require knowledge of the array geometry and does not involve an exhaustive search, which is correct. I mean, this first part here does not require knowledge about the array geometry is partly correct, but yeah, because this esprit algorithm really does not require the whole geometry of the array, require only part of it. Yeah. So this is the, I would say also true somehow. Yeah. And then it does not require this exhaustive search, which is also true. So I would say this is really a good answer. Then let's move now to the next experiment, which is augmenting the query. So since now here we got a good answer, maybe you will not see that difference now that much, but I run really into cases where augmenting the question will make the difference. So let's go through this quickly anyway, and then you can try it and decide for yourself if this is something helpful and you would like to use or not. So as I'm mentioning here in the comments, so there are two ways to actually to make query augmentation. So first, you reformulate the question and then augment with that, or you ask the LLM to answer the question and then augment the answer. So for the second one, I would say you should know your LLM which you are using first. So if this LLM can answer the question roughly, then it's okay. Then you can really do this. If your LLM does not know the subject and the answer will be wrong, then doing this actually could hurt you instead of helping you, while the reformulation of the question would work most of the times. So doing the reformulation is really simple. Also the answer, by the way, so you just want your LLM to answer. Let's go now through the reformulation because this is what I am showing here. So we are using again generate the same model. I'm using here streaming equal false because anyway you don't want to return this to the user anyway. And we are using the same option, so temperature 0. And as you can see, the prompt is really simple. So rephrase the following question, then point in the question, and then I'm putting the rephrased question just to make the LLM start with the reformulation, yeah? And then printing the response. Let's run this. So remember the question was, what's the esprit algorithm for direction of arrival estimation? So the reformulation is, what's the esprit algorithm used for estimation the direction of arrival in wireless communication systems, which is, I would say, an okay formulation. But in my opinion now, for example, the question itself was better than the reformulation, even though I will augment it and you will see that in our case, since the question is okay and we got the answer like directly, this reformulation will also give you the correct question. It will not hurt. But as I said, I've seen many cases where that actually helped me. I mean, I was like using 100 PDF files and the question there was about taxes and so on. It was really helpful. Let's see now how we'll use this. So we now have our response here, which is this reformulation of the question. So we simply use it in the query now. So in the query, instead of passing only the question, we pass the question and also we append the response to it, which is this new reformulation. And we are again asking for 10 results as before, the same. So we're printing the distances and the information of the first document. And then again, we have the prompt. It's similar to before. So you are a helpful assistant, and so on. And those are the given context. And then this is the question, and let's start answering. So it's really the same as before. It's also generate, and then we are printing the response. Let's see. And now we got the answer. The estimation of signal parameter via rotational invariance technique algorithm is used for direction of arrival in array signal processing. It doesn't require knowledge of the array geometry and does not require also an exhaustive search. So it's really the same answer as before. So as I said here, because the question was really formulated in a good way. So what you can do also is that you can ask the LLM for multiple reformulation, for example, and then appending all those. You can also ask the LLM, as I said, to answer if you know that the LLM already trained on similar data, and then you can also append the reformulations and the answer. I mean, that's up to you, and that's, to be honest, use case dependent how this can help you. So that's all I wanted to show in this video. I wish you really the best for your RAG application and hope to see you in the next video. Bye.